All right. Good afternoon, everybody. This is Mrs. Masteller, and I'm coming at you trying to teach you about section 4-4 today, which is titled Complex Numbers and Roots. So a complex number essentially is just what we call an imaginary number. All right. So I warned you of these before in the past that there is a such thing as an imaginary number, and it kind of gives you some details here at the top, and these are just things that you eventually are going to have to memorize. Just knowing that if you take the square root of -1, you get I, and that I squared is -1. And one is actually derived from the other one. So if you know the fact that I is equal to the square root of -1, just think about it like this. If you square both sides of the equation, because whenever you do to one side of the equation, you have to do it to the other, you would have I squared is equal to, when you square a square root, these are basically inverse operations of each other. They cancel each other out, which is how you end up with that I squared is -1. Okay, so this one is basically derived. It comes from knowing just that first fact, knowing that the I is square root of -1. Okay, but again, eventually over time, you will have these two facts memorized because we're going to be using them a lot all throughout this section. So let me give you an example. Looking at problem number 1, it says to simplify, express each number in terms of I. So if you wanted to take the square root of -49, well, you could separate this out into being the square root of -1 times the square root of 49. Okay, if you multiply those together, the square root of -1 times the square root of 49, that's just the same thing as the square root of -49. When we know the square root of 49, that's just 7. And now we know the square root of -1, and that's just I. So if you combine these two together, your answer would just be 7I. Okay, so when we say 7I, we don't say I7. So again, anytime you have a variable, typically it always comes afterwards. So just like, we say 5x, we don't say x5. Same exact idea. So the number should always be first, and then the I should be at the very end. Okay, that's just the proper notation, that's the proper way to write it out. But if you have something like the square root of -28, so 28, if you separate this, same idea as the last one. I'd have the square root of -1 times the square root of +28. Okay, but 28 is not a perfect square, not like 49 was. So we'd have to break down 28 by hand, which you could do this one of two ways. Let me just kind of highlight this for you. I'm going to do it both ways just to show you guys how you can simplify a radical. But square root of 28, you can separate this out into 4 times 7, where we know the square root of 4 now. So if you choose 4 times 7, that's just going to be 2, and the square root of 7 would still be left over. So you'd have 2 square root 7. And then again, we know the square root of -1, that's just I. So if you combine these two together, you would have 2I square root 7 as your solution. Okay, so some students ask too, well, why can't I say 2 square root 7I? Well, because if you're, a little bit of a sloppy writer, if you extend that too far, then it looks like the I is underneath the radical. So whatever simplifies, you want to make sure you pull that out front. So again, that would be the 2 and the I. Bring those out front of the radical, and then underneath the square root, you'd still have 7. So again, that's one way you can simplify a square root. Another way you could break down the square root of 28. So maybe if you started with something besides 4 and 7, and let's just say you started with 2 times 14. Okay, so if you're breaking it down to basically prime factors, so 2 you would stop there because that's prime, but breaking down 14 into 2 times 7, well, now you see that you have 2 square root 2's, right? So since it is a square root, you're looking for pairs. These pair up, you have 2 square root 2's, which would just come out as a single 2, then you'd have a square root of 7 left over, which is the same thing that we had over here. 2 square root 7, 2 square root 7, same exact idea. Okay, so either way you look at it, it still breaks down to be the same thing. So let's try it with the next one. We have the square root of -32 over 4. So the square root of -32, let's just simplify that first. Let's focus on this. So square root of -32, let's break this up. It's a -1 and then +32. Okay, so breaking down 32, again, you can either do it like I did with the 28, think of the biggest perfect square that goes into it, or you can do it kind of like a factor tree, going all the way down to prime factors. But the square root of 32, I can just simply say 16 times 2. So the square root of 16 times the square root of 2, because I know the square root of 16, that's just 4. So that would just be 4 square root 2. And again, the square root of -1, that's just I. So if I bring these two together, combine those two, this would be 4I square root 2. and that's all over 4. Okay, but you can still actually do a little bit more work because the 4's actually cancel. They reduce down, divide each of them by 4, where we're just looking at I square root 2 as our final solution reduced. Okay? For number 4, you have 5 square root negative 144, so you can even think about this as like 5 times the square root of negative 144. So just think about what's the square root of negative 144. So if I break this up into negative 1 and then positive 144, we know the square root of 144 is 12. Again, this would just be I. So it'd be 5 times 12i basically, which comes out to be 60i. So you can multiply a real number with an imaginary number. You could still do that, just like if it was 5 times 12x, that just gives you 60x. Similar idea. Okay, so for number 5, if you had to multiply 4i and 5i, well, 4 times 5 is 20. I times I is I squared. But what's I squared again? Up here at the top, it says I squared is negative 1. So anytime you get I squared in your solution, you should always swap it out with what it is, and that's negative 1. So anytime, as soon as you see an I squared in your solution set, take it out, replace it with what it really is, and that's negative 1, where our final answer would actually be negative 20 in the end. Okay, so for number 6, similar idea. So negative 3 times, or negative 3 times 2 is negative 6. I times I again is I squared. Swap it out though. What's I squared? That's negative 1, where our final answer would actually be positive 6. Okay. Number 7, breaking down these radicals. Let's start with that. So square root of negative 12. I'm break this up into negative 1, positive 12. Breaking this down, I'm going to choose 4 and 3 because I know the square root of 4, that's just 2. So that'd be 2 square root 3. But again, square root of negative 1 is I. So this is actually 2i square root 3 once you simplify it. So all this work, again, the square root of negative 12 simplifies all the way down to 2i square root 3. And now if I break up square root of negative 2, maybe into negative 1 and 2 again, but you can't really break down the square root of 2 anymore, so that's just going to stay square root of 2, but I can still pull out the I to make this I square root 2. Okay, so this one simplifies into I square root 2. Okay, now I need to multiply these two together. I simplify the radicals, but now multiplying them, what is 2i square root 3 times I square root 2? Well, 2i times I, you multiply the things out front of the radical first, multiply those terms. So this would be 2i squared. Now multiplying square root of 3 times square root of 2, that's a square root of 6. But again, I squared, which is negative 1. So I take that out, replace it with negative 1. 2 times negative 1, our final answer is going to be negative 2 square root 6. And that's your final solution. Okay, so basically I simplified the radicals first, and then I did the multiplication at the very end. But you want to keep simplifying, simplifying, simplifying until you cannot anymore. But looking at number 8, so we have 1/3. It's kind of similar to the one right above it, but it's 1/3 times the square root of negative 81. Well, square root of negative 81, just think about it. Negative 1 and positive 81, or that's just 9 and this is I. So we're really doing 1/3 times 9i. Which, if you wanted to, with multiplication, that'd just be 9i over 3, and then just simply reduce it. So 9 and 3, you could divide those both by 3, so it'd be 3 over 1. So you get 3i over 1, or just 3i in this case. Alright, so we're seeing how I kind of works out. Again, just knowing these two facts, I was able to work through all 8 of those problems with no problem whatsoever. So just knowing that I is the square root of negative 1 and I squared is negative 1. Doing the same thing using those two facts for down below here. There's a couple different ways you might see these worked out. I'm going to show you kind of a different way as to what they are illustrating in these problems, but you know that I to the first. So I to the first power is obviously just I. And we know that I squared is negative 1. But using this base for each of these problems, you can find I to any exponent. So as we see down below, we have 6 more examples where we're trying to find I to any power. So let me just kind of show you how this is done. So even look at the next one. What is I cubed? I cubed is honestly the same thing as I squared times I. So those are the same exact thing. So if I do I squared times I, that is the same thing as saying I to the third power. But again, I squared is negative 1. So that's why you see negative 1 times I now. So instead of the I squared times I, now it's negative 1 times I. And what's negative 1 times I? You get negative I as your solution. Okay? And I to the fourth power, well, I can take I to the fourth power, I can swap that out with an I squared squared. So I squared to the second power. If you have a power to a power, you multiply those exponents, and that gets you back to where you just started with the 4. 2 times 2 is 4. Okay, so now basically the laws of exponents, you got to know how the laws of exponents work. But again, a power to a power, multiply them, get you back to where you just started. Where, again, I squared, you just swap that out with what it is, which is negative 1. Now you're just doing negative 1 squared. Negative 1 squared gives you positive 1 as your final solution. Okay, so it might seem a little confusing at first, but trust me, it's not as difficult as it looks. Okay, let me kind of show you with number 9. So if I wanted to show you how to work out, how do you simplify I to the 6th power? So evaluating powers of I. So I'm just going to replace I to the 6th power with an I squared cubed. Okay, so I'm using I squared as my base, and that's what I always do for these types of problems. I always refer to I squared as my base because we know what I squared is. I squared is just negative 1. Okay, so I squared cubed is the same thing as saying I to the 6th power. Once again, a power to a power, if you multiply those, that is 6, right? That'll get you back to where you just started. Okay, so I'm going to take out I squared now and replace with what it is, which is negative 1 to the third power. Well, now I just need to calculate what is negative 1 to the third power. Essentially, I'm asking you what's negative 1 times itself 3 times. So what's negative 1 times negative 1 times negative 1? That'll just be negative 1 as my solution. And that's it. Okay, so for number 10, similar approach. If I have I to the 26th power, that's the same thing as saying I squared to the 13th. Those are the same exact thing. I to the 26 is I squared to the 13th. Again, because 2 times 13 gets me back to 26. Okay, but now taking out I squared, because I squared is just negative 1. So now our question is, well, what's negative 1 to the 13th power? Negative 1 to the 13th power, again, that's essentially doing negative 1 times itself 13 times. But instead of writing it out, you should know that if you have a negative 1 as your base, and if this is an odd exponent like it was for the last one, odd exponent, your answer is just going to be negative 1. So if I multiply negative 1 times itself, again, 13 times, it should just be negative 1. Versus if I were to have something like negative 1, let's just say to the 12th power, or even if I had negative 1 to the 14th power, so if it was an even exponent, these would be positive 1. Positive 1. So if you have a negative base, even exponent, it'll be positive. But if you have a negative base with an odd exponent, the answer should be negative. Okay, I'm going to skip 11 and 12. I'll come back to those. I want to do another even exponent before we move on to odd. But I to the 40th power, that's the same thing as I squared to the 20th. Those are the same exact thing. Okay, there is no difference whatsoever in this problem. I to the 40th is the same thing as I squared to the 20th. Again, take out I squared now, replace it with what it is, that's negative 1. And now what is negative 1 to the 20th power? Well, again, if I have a negative base and an even exponent, it's going to be in positive. Positive 1's our solution. Okay, so those weren't too bad. But now what if you have an odd exponent like 45 or 35 or 63? How do you evaluate these? So what you want to do first is you want to make it into an even exponent. Here's how you do that. Take out an I, which is going to reduce it by 1. So instead of I to the 45th power, now we have I to the 44th. Okay, but again, this is technically the same thing. I to the 45th is the same thing as having I to the 1st times I to the 44th. Same exact statement. Okay, now that we have an even exponent, you want to break this guy down now the same way that we just did the previous 3. Okay, but keep that I out front. Keep that I to the 1st power. But break down I to the 44th into I squared to the 22nd. Okay, now take out I squared with what it is. That's negative 1 to the 22nd. Evaluate what is negative 1 to the 22nd. Well, that would just be positive 1 because it's an even exponent, so it should be positive. And now what is I times 1? It'll just be I is your solution. Just positive 1I. Okay, so same thing for number 12. Force this to be an even exponent first. How do we do that? Just take out 1I. So now you got 34. Okay, break down now the even exponent the same way we just did the other 4 problems. So you're going to keep that I to the first in front, but break this down into, that'd be I squared to the 17th, because 2 times 17 is 34. Again, replace the I squared. Keep that I in front, but replace this with negative 1 to the 17th. Okay, now evaluate what is negative 1 to the 17th. Well, that's going to be negative 1 this time because it's an odd exponent, which just gives me negative 1I as my solution. Okay? Last one, 14, another odd, but again, just make it into an even, pull out that 1I, and now you got one less, 62. Okay, break down 62. So keep that I to the first power out front. This would just be I squared to the 31st. 2 times 31 is 62. All right, swap it out now. Take out I squared. So that's negative 1 to the 31st. Now what's negative 1 to the 31st? Evaluate that. And that would just be negative 1. So you got an odd exponent, so it'd be negative 1. Again, multiplying these two back together, you get negative 1I. And there you go. Okay, so if you notice, kind of highlight something here. Change my color so you guys can see what I'm talking about. If you notice, if you have an even exponent, look at the types of answers that we got. Even, and then even. Okay, so when you have an even exponent, your answer is either going to be positive 1 or negative 1. Versus if you have an odd exponent, let me change my color again. If you have an odd exponent like I to the 45th, our answer was I to the 35th, answer was negative I, and I to the 63rd, we got negative I again. So if you have an odd exponent, your answer is either going to be I or negative I. So you have one of 4 possible solutions, either positive 1 or negative 1, or positive I or negative I. Okay, so keep that in mind when you're working these out later in your examples. Okay, moving forward here, on to the next page. So it says equations with imaginary solutions. Solve each equation. Okay, I'm going to point out to you guys that these are not factorable. There's no way, shape, or form that you can factor and get to a solution because our solutions are going to be imaginary. So we're going to use something that's called the square root property. So again, even if you tried to factor it, let's just say you went ahead, you added 144 to set this equal to 0. Again, what you're going to come across is something not factorable. If that said x squared minus 144, you could factor it, okay, where you have a difference of squares. But we do not have that. We have a sum of squares, technically, which doesn't even exist. Okay, there's no such thing as a sum of squares. You can't factor that whatsoever. So what we're going to have to do, like I said, is use something called the square root property, where all you'd have to do from here is take the square root of both sides. Okay, that's using the square root property, because whatever you do to one side of the equation, you have to do to the other. And why am I taking the square root? Because that's how you undo something squared. To actually solve this for x, to get x by itself, I need to take the square root. Okay, so I get x by itself is equal to, but here's the kicker. When you take the square root of both sides of an equation like this, you actually get positive and negative solutions. So now you want to ask yourself, well, what is the square root of negative 144? That's 12i. So these would be my 2 solutions. Okay, so if you plug 12i, positive 12i or negative 12i back into the original problem, you will get negative 144. And again, if you don't believe me, plug positive 12i in. You have 12i squared, and that should equal negative 144. Well, square the 12, square the I, that's 144i squared. And that should be negative 144, and it is because, again, I squared is just negative 1. So if you have 144 times negative 1, that's going to be negative 144, so it all checks out. Okay, and same thing too, even with negative 12i. If I plug that in, if I do negative 12i and I square it, that's also going to be negative 144. Because if I square negative 12 and if I square I get positive 144i squared, which is the same thing that we just previously had. Again, I squared, that's negative 1, which is also going to be negative 144. So they both work. Okay? So whenever you take the square root of both sides of an equation like that, you should get two solutions, both positive and negative. So number 16, similar approach. But start off, divide both sides by 4. So basically you get x squared by itself. So you have x squared equals negative 25. Now take the square root, where you get x is equal to positive and negative 5i as your solution. 17, so getting x squared by itself, start off, subtract the 28. So we have 7x squared equals negative 28. Divide by 7, so x squared is negative 4, and then square root it, where you get x is positive negative 2i. So same thing for 18, similar approach like number 17. Start off, just move the 90. So I'm just trying to get x squared by itself. So I have 5x squared equals negative 90. Divide both sides by 5. So we get x squared equals negative 16. And now square root both sides. So negative 16. That's going to be 5. Actually, that's negative 18, isn't it? It should be negative 18 instead, not negative 16. But square rooting both sides, you get x is equal to, well, now we have to break down the square root of negative 18. So I'm going to do 9 and 2. So again, I'm going to do 9 times 2, where that's just going to be 3 square root 2. But again, given the negative 1 as well, the square root of negative 1, which is going to be I, you get plus and minus 3i square root 2 as your two solutions. So positive 3i square root 2, negative 3i square root 2. Okay, so that's just using the square root property again, just solving basic, where you obviously have I as your solution. Okay? A complex number. Just basically know a complex number is written in this format. So a complex number, it's kind of a mixture between a real number and you have an imaginary. Okay, so the real number you always want to write it first, and then the imaginary should always be kind of tacked on at the very end. Okay? These next examples, we don't really do these anymore, so we're just going to kind of skip this section. Okay? We'll come back to talking about complex numbers here soon enough. But these next examples, it says you're going to be adding and subtracting complex numbers and then write the result in a plus bi form. So again, that's just the proper form that you always want to write it in. You want the real number first, followed by the imaginary. Okay? So looking at number 22. When it comes to adding and subtracting with complex numbers, you basically just want to combine like terms. So think of I just as any other normal variable. Okay, think about it like that. So the only like terms you have for 22 are the 5i, and then you're adding negative 6i. So that would just be negative 3 minus 1i, and that'd be your solution set. So again, that is in a plus bi form, where you have the real number first, followed by the imaginary. Okay, and that'd just be it. 23, we're subtracting, so we have 2i, we're subtracting from it 3 plus 5i, so you almost have to distribute this minus sign to both terms, making this 2i minus 3 minus 5i. And again, now just combine like terms. These are only like terms that we have, but it has to be, like we said, an a plus bi form. So I would want to write the real number first, which is negative 3. Now combine the imaginary numbers, so 2i minus 5i, which is negative 3i. Now it's in the proper form. Okay, number 24, adding these two. So like terms, our real numbers first, that would just be 8. And then if I have 3i and I'm adding to it negative 3i, well, those just cancel. My answer would just be 8. 25, we're subtracting again, so I would go ahead and distribute that minus sign, making this 5 minus 2i plus 2 plus 3i. Now combine like terms. 5 plus 2 is 7. Negative 2i plus 3i, that'd just be 1i. So 7 plus I. Okay? Multiplying. So how do we multiply complex numbers, simplify, and write the result once again in a plus bi form? So if you want to multiply with an imaginary number, number 26, just distribute right here, right? So I'm going to multiply 2i times 3, 2i times negative 5i. So 2i times 3 would be 6i. 2i times negative 5i would be negative 10i squared. Okay, because I times I gives me I squared. Now, well, I see an I squared in the problem, so I want to take that out. Again, anytime you see I squared, replace it with what it is. That's negative 1. So I'd have 6i minus 10 times negative 1. Well, negative 10 times negative 1 would be positive 10. But now it needs to be in a plus bi form. So if you just do a little switcheroo, positive 10, positive 6i, so it'll be 10 plus 6i. Okay, 27, when you have two binomials, if you will, what you'd want to do for these ones is FOIL. So you want to do the first or the full FOIL effect here. First, outer, inner, last. So 4 times 6 is 24. 4 times negative I is negative 4i. Negative 4i times 6 is negative 24i. And then negative 4i times negative I is positive 4i squared. Okay, so we got a lot of fixing to do for this problem. We got some like terms here, and we got an I squared over here in the back. So you'd have 24, that'd be minus 28i plus 4 times negative 1, which would be 24 minus 28i minus 4, technically. 24 minus 4 is 20, and then minus 28i. So again, it's an a plus bi form where you have the real number followed by the imaginary number. Okay, so 28, last one on this page. Again, foiling these two together, this would be 9 minus 6i plus 6i minus 4i squared. Okay, again, fixing this one up. Combine these like terms, so you'd have 9. Well, those just cancel, negative 6i plus 6i. Then you'd have minus 4 times negative 1. So replacing my I squared again. So that'd just be 9 plus 4, which gives you 13 as your final solution. All right. So we've seen how we add and subtract, how we multiply imaginary numbers. The last thing we have to talk about is what a conjugate is, which is kind of illustrated in this very last problem. Last one that we did, that 3 plus 2i, 3 minus 2i, those are conjugates of each other. Okay, and you even see something kind of special happen when we multiply by the conjugate. When you multiply any number times its conjugate, the i's basically eliminate. You just have a real number as your solution. We just had 13. And that's typically what you're looking for. Okay, so if you had to identify the complex conjugate, it just says define each complex conjugate, which technically represents the other solution. So again, if you have a plus bi, the conjugate is just simply a minus bi. And same thing vice versa. Okay, so if I'm looking at 9 minus I, if that is my complex number, the conjugate would just be 9 plus I. That's it. Okay, 30 though, what you'd want to do first, it's not in the proper form right now, so if you switch these two around, it should be square root of 3 plus I. Okay, now we want to write the conjugate, which should be square root of 3 minus I. That's the conjugate. Okay, 31, they give us negative 8i. The conjugate would just be positive 8i. So you can even think about this as like 0 minus 8i, or the conjugate would be 0 plus 8i, or just positive 8i. Okay, since you don't have the real number to your complex number, it would just be 0 in that case. And 32, the last one, so again, it's not in the proper form, so make sure you rewrite it, put in the proper form, it'd be 7 plus 5i. Now identify the conjugate is 7 minus 5i. And there you go. Okay, we no longer actually do division anymore, so we're not even going to worry about these last few examples. We just put in a big X through that. We're not going to be doing division either. Okay, so that's the end of this section. That's it. That's all we have for you. So as usual, if you do have questions, let us know. Otherwise, have a great day.